you. I'm Shimon Ben David. I'm the Chief Technology Officer for WEKA. As Stephen probably know, I'm here year after year. So I'm in the company for the last 8 years, actually based here in the US. What I wanted to do today is to talk about WEKA. Kind of cover a bit of what Colin mentioned. What were the design considerations when we designed WEKA? How are we doing this? And then what does it allow customers to do? And I'll spend a fairly large amount of the time on how are we doing the things that we're doing. So when we look at movement to the cloud, we see that a lot of organizations are adopting cloud native approach. So we can't just take our current existing working environment and throw it to the cloud as is. We want to adapt to the cloud. We want to make sure that our workflows, our pipeline, our DevOps orchestration is suited for the cloud. And so what is a cloud native approach? Basically, it's a very dynamic, elastic, fast approach, right? You want to make sure that you can utilize public clouds, private clouds, and more. You want to make sure that you're utilizing dynamic environments, containerized environments, so you can bring up environments, demolish environments as you need them, and not just have monolithical environments up and running when you don't need to. And you want to make sure that you're using an elastic infrastructure, again, that can allow all of that. And eventually, the value of a proper cloud native approach is speed up execution and delivery. So that's the value. So if we can move to the cloud, if organizations are adopting the cloud, and as we see, a lot of CIOs, a lot of organizations have that as a mandate to move to one or more clouds, then that's the value, speed up execution and delivery, and definitely punching up on the cost properly, right? So what were the design considerations for WEKA? So with WEKA, that is a bit of a buzzword compliant phrase, right? Multi-dimensional performance, multi-cloud native environment. So when we created WEKA, we wanted to make sure that we're not creating another me too, we're not creating another storage environment. We actually created a data platform. What does it mean? We created a data platform designed for clouds, flash, and object. What does that mean? So when we created all of our data structures, algorithms, data layout, distribution, protection, everything was designed for flash from day one. Flash and integrated with an object environment. So you'll see that some of the things that I'll mention about how we're doing what we're doing can only be done if you designed your environment from day one to that coupled integration. In addition, from day one, we're running on AWS Cloud because, simply put, we also adopted that cloud native approach in our development. So our product run on AWS, our regression, our QAs, a lot of our development. So we kind of like ate our own dog food and our own messaging to provide it to customers. So our data platform is designed for clouds, flash, and object from day one, and that allows us the capability that I'm going to show. As Colin mentioned, broad multi-protocol access to all of the data, or simply put, all protocols to all data. When we look at modern pipelines, what we're seeing, and my colleagues will talk about it further, we see that there's a large request, high request for facilitating an entire pipeline of activity. Definitely when going to the cloud, when leveraging IoT devices to send data to object stores, we wanted to make sure that you can communicate with all protocols so you don't need to move the data between different storage environments on-prem or on the cloud. So imagine throwing data into WEKA using one protocol on the cloud to a cloud WEKA at a certain protocol, for example, S3, and then crunching it, analyzing it in a high-performance fashion, as we'll see in a bit, in other protocols, without the need to move it constantly. Performance for bandwidth, IOPS, low latency, and metadata. That's one of the outcomes of the design points that we wanted to create, and I'll talk about how we're doing that, but that's uniquely differentiating. So the ability to say, when we talk about performance, it's not only how many gigabytes per second can we do on the data, it's how many gigabytes per second, how many millions of IOPS on the same data set, at what metadata performance, and at what low latency. So for example, in the cloud, we can provide low latencies as 100 and a bit microseconds per IO, for example, for 4K read. And on the same data, we can provide terabytes per second, as Colin mentioned. So that's uniquely differentiating because eventually it enables the fourth bullet here, faster than local disk for mixed workloads. So when you look at a modern workload that is not designed for one specific application, your data goes through a lot of transformations. It goes through a lot of changes in the I patterns, in the file sizes, in the file size numbers. And we see in classic HPC environments or in other legacy environments where data is being moved, much in the same way that data was moved due to different protocol requirements, data was also moved due to different performance characteristics between different storage environments, even on the cloud. So the ability to say, we're going to provide that massive performance in all aspects of I/O patterns, throughput, latency, IOPS, and metadata. Actually, the end result is faster wall clock time for a customer that doesn't need to move the data and just get higher performance.
So when it comes to these performance numbers and these claims, when it comes to customers actually utilizing it, do you provide SLAs? Do you provide guaranteed levels of performance on that?
Definitely. We have, I will talk about how we design the WEKA system. It makes it very predictable. And we actually have sizers that are showing you if you're using, for example, for the cloud, for the AWS cloud, these instances, that amount, you're guaranteed to get that amount of performance. What are the design points when creating WEKA? What we're seeing here is a rough architecture. We're seeing here compute instances running the WEKA client component, and we see here actually instances running the WEKA environment. So when we create the WEKA environment, what we're doing is actually we're just instantiating instances that contain local NVMEs. This could be the i3ENs, this could be some other instance types. The only thing that we require are these instances with their NVMEs. You'll see in a bit, we don't require any other AWS services. For example, this is an AWS example. We'll see a GCP and an Oracle example in a bit, but we don't require any other services. We don't require, for example, EBS. So we see other storage environments that are connected with EBS. We don't need that. We use the instances local store. WEKA is being built from day one on-prem and also on the cloud, definitely, to scale out. So when we need more capacity, more performance, we actually just scale out the amount of instances. How do we do that? And this is a key consideration. Metadata is distributed evenly across all of the WEKA nodes. And we're actually running thousands or tens of thousands of virtual metadata servers. What does it mean? This is a WEKA cluster. There's no different instances that are performing different activities. In terms of metadata handling, each of these is running a number of cores, and we have multiple types of software entities in our environment. Some of them are running virtual metadata servers. So each of these instances is running a fair amount of virtual metadata instances, and eventually it translates to thousands of virtual metadata instances running across the environment. Why is that important? Imagine that we take all of the namespace. Could be terabytes, petabytes, exabytes. Could be that we have a namespace that spans only on the flash tier, or a namespace that spans between the flash tier and the object storage tier, which I'll talk about in a bit. What we're doing is, imagine that we carve that namespace into thousands of small pieces, and each of the virtual metadata servers on these instances is handling their own respective part of the namespace. So now we don't have a notion of a metadata server or a head node that is handling part of the activity. Accessing thousands or millions or billions of files is now being handled by all of the instances that are participating in the cluster. So
I want to just back up a little bit here from a consumer standpoint.
Yeah.
I'm a customer. I want to use WEKA.
Yeah.
Am I spinning up my own infrastructure that's going to run all this, or am I consuming WEKA as a service and you're running a multi-tenant architecture that looks like this?
Question, you're actually spinning up your own environment. And when we talk about autoscaling group, you can connect it to your own DevOps environment that autoscales it up and down. We do have customers that are looking at it as a managed service as well. But because you'll see that WEKA is really software as code, we see a lot of customers actually integrating it to their own cloud orchestration.
Okay, so this is not a
your
service
VPC.
you're providing.
Exactly.
It's a software platform you're providing and a way to deploy it. And then it's up to me to manage it going forward. But it's also single tenant. I'm not sharing this environment with anybody else.
Exactly.
Okay.
By the way, you as a customer can create a multi-tenant environment for your organization. But
Sure.
Yeah, so we're paying for thousands of virtual servers when we do this?
No, you're actually paying for a number of instances, And within these instances, by the way, we have customers running as low as 6 instances or more or less. And within this, we're actually running our own virtualized thousands of virtual metadata servers. I'll give you an example. Let's say that you're running 6 instances, 6 i3en instances in any shape, 2x, 4x, 16x, doesn't matter. We're likely running anywhere between 500 to 5,000 virtual metadata servers across them. What does that make sense? What does that mean? Imagine that we're running 5,000 virtual metadata servers, and you have, I don't know, 1 or 10 or 1,000 instances consuming that file systems. If they write 5,000 files, each of these will be handled by a different virtual metadata server. So the scale out capability is scaled out across all of the storage node, and each of them is always taking an equal part of managing the metadata. So if I'm writing millions of different files, or even if all of them, consider like an HPC problem where you have like an into-one checkpointing, where you have thousands of cores hitting the same file in different block ranges, each of them is even handling its own different block range within the same file. Okay, so that's very unique. It allows us to provide massive metadata performance, make sure that it's predictable. To your question, metadata performance is very predictable because it's always fully utilizing what the instances can do. So there's no IO pattern that says maybe I have 10 instances and maybe 5 of them are loaded more than the others. That won't happen because metadata is always being handled across all of them, and performance scales linearly, and we get more resilient at scale. I'll talk about this as well, but sufficient to say that what we did, and I'll talk about our own block layout as well, our metadata environment is actually using our own block layout to make sure that the metadata servers are not communicating with each other. So a lot of the problems that you have with metadata scaling is when you add more, and we see that in other environments as well, is when you add more and more nodes, suddenly the metadata nodes between them has the east-west chatter. They need to coordinate, they need to switch token between themselves. So eventually, as you add more and more metadata servers or nodes that are acting as metadata, the east-to-west chatter is actually gives you the diminishing result, and there's a limit to how much you can scale. With WEKA, one of the key design points is that the metadata servers, these thousands of virtual metadata servers, are not communicating with each other, and they're using, and in order to still be resilient in case of failures, what they're doing is they're journaling constantly to our own highly protected, highly performant block layout. And in that case, if some of them are failing, we're actually able to just bring up others and continue from the same place. Okay, so that's metadata handling at a high level. That's how we can scale out metadata as well. Yeah.
Can I just ask a couple of points of clarification? You've said there that it scales linearly. So these nodes are disaggregating the storage from, say, performance? Is that fair?
They are providing the performance.
They're providing the performance.
They're disaggregating from the compute. And
do each of these nodes have access to all of the underlying storage then?
I'll talk about it, you'll see.
Okay.
These nodes, and let me, I'll start by answering that, and that's also this part. These nodes contain their own local instance store, right? Their own local NVMEs on the cloud. What we're doing is we're actually, if I'll take a step forward, and I think it will answer, whenever an IO goes into the system from any of the clients, what we do is we break it into 4K pieces. So imagine even a single instance writing a 1 meg piece into the system. First of all, it would consult the metadata servers to know where it would actually know where it needs to go. And then what it would do is the data would be broken into, for example, if it's a 1 meg file, 256 4K pieces. And these 4K pieces are striped and protected across all of the local instance store. So there is no data locality. There is no one node contain a file or it needs to go here to get a file, because a file is by definition striped across all of them in 4K pieces. So I don't need to go to another node and bring it. I have part of it, you have part of it, they have part of it. When I'll need to read that 1 meg that I wrote, I'll go and get it from all of them in parallel. So the client is acting only as a client. It's aware of the metadata of all of the environment. it's aware of the block layout of all of the environment. When it's writing to all of them. When it's reading from all of them in parallel. So there's no notion of I'll go here and it will go and bring it to me, or you don't need that.
But to massively simplify it could be one S3 bucket underneath.
Let's talk about S3 in a bit. I still didn't mention S3.
Okay.
This is the flash layer. And the unique thing again is that everything is in 4K pieces on the flash layer. And you don't need to choose, when we talk about always providing all of the performance, you don't need to choose whether you're doing throughput or IOPS. So for example, in other environments, when you format a file system, you need to choose the block size. With WEKA, you don't need to, because everything is in 4K and everything is across all of them. And everything is accessed in parallel for metadata and for data. When we are using S3, and S3 is an optional component, by the way, but we see a lot of customers using it for multiple reasons. What we're doing, and actually, as we like to say it, we actually wrote 2 parallel file systems to begin with. We wrote the flash parallel file system, and then we wrote the parallel file system that destaged the data to the S3. So I'll give an example. Imagine that you have a customer that is running, and I think this is actually a real example, maybe we'll even mention it, customer running a 10 petabyte file system where 10 petabyte are an object store capacity, and 1 petabyte approximately is a flash capacity. Mm-hmm. What we're doing in that case, everything still holds. Metadata is always on the flash tier. Actually, maybe I'll even show that. Metadata is always on the flash tier. Data always lands on the flash tier. And then as we have our own algorithms that decide when to move data between the flash tier and the object storage tier. Okay. And then according to that, we provide the data. The compute clients are mounting the WEKA system. They don't need to know about the object storage tier. Object storage tier can grow and shrink. These guys can grow and shrink. I'll show it in a different slide. And they're not even aware of it. We do the decision of when to move it back and forth. We have some prefetch, manual, and automatic. We're able to do that. The fun thing is that because metadata is always on the flash tier, then if you're familiar with POSIX, sometimes 60 to 70% of the IOs are metadata. So even if the majority of your data is on the object storage tier, when we now need to go and bring it, 60 to 70% of the IOs are being handled from the flash tier. So that's massive performance.
Obviously, all of this is part of your infrastructure that is initially present on all the different regions to obviously serve all of this. So
this would actually be on a single region.
Yeah.
We will actually show an example where you have also a WEKA across multiple regions.
The question I want to ask is there a minimum footprint that you actually deploy on all the regions that you serve? So is there a minimum footprint?
So a customer would deploy that on where he's actually working. So if I'm working on 1 or 2 or 3 regions, I might have a different WEKA cluster of 6 instances. That's the minimal footprint, maybe per each of them. Then maybe each of them is a different distinct cluster, or maybe there is one aggregate cluster across them.
And every customer gets that footprint to themselves, like 6 of them.
Definitely.
So that's your minimum footprint.
Because we're fully software defined, we provide only the software. We also provide a lot of the cloud, and I'll show that in the next slide, the cloud formation, the orchestration, the Terraform, that shows the customer how to do it. So it's kind of like a next, boom, you have a WEKA cluster. But yeah, every customer has it for themselves.
Right. Okay. Thank you.
So what we allowed when we created that flash and object store coupling is we allowed for actually to create a better total cost of ownership, right? Because now I'm combining my instance capacity and my object store capacity to create petabytes of capacity at an S3 pricing scale. It also allowed to create backup DR and bursting, and if I have time, I'll actually show that as well. As we mentioned, all metadata always stays on the flash tier. So no matter if we move the data to the object storage tier, all metadata is always on the flash tier, and that's massive. What we're doing is we know that object stores actually benefit from large files. So even though everything under the hood in WEKA is in 4K pieces, again, giving you that massive throughput and massive IOPS, when we destage data to the object store, we actually aggregate that in larger chunks, in 64 meg chunks. So for example, if a user wrote a file that is 640 megabyte, we'll chunk it into 10 objects and drop that into 10 objects. So we get massive performance from the object stores as well. We actually squeeze as much as they can provide in many cases. by working with large files. When we read these files,
Traditionally, with object stores, we've seen reduced performance.
Reduced than a
Even on
flash.
highly capable
Mhm.
systems, you know, if NFS was 2 gigasecond and NFS of already maybe was 8, object might only be 1. How
yeah.
well does your object store performance scale?
We're seeing gigabytes per second from object stores,
Okay.
right? Object stores are in modern object stores, depending how you actually also integrated with the underlying object store layout. So eventually how you lay out the bucket, how you lay out the object structure. We actually did work on optimizing that for the AWS layout as well. You're able to get a lot of throughput, not a lot of latency. Latency is actually 20 milliseconds up to first byte. But because we're doing a lot of prefetching, automatic and manual, depending on the customer, because we designed our system for all of the nodes to parallelize that, there's no object store gateway. Everything is parallelizing the access. So maybe I'm working with one file, but suddenly 10 instances are now getting massive amounts of objects in the background. So we're actually saturating a lot of object store performance.
So you abstracting multiple S3 buckets too?
So by default, yeah, you can have multiple file systems that you created on a WEKA cluster, and each of them could be connected to a different bucket, or I'll even show in the next slide to more buckets.
But can it be addressed as a single object store?
Yeah.
Okay.
Definitely. Even though we have these large files, these large chunks on the object store, when you need parts of it, because we do want to be IRPS friendly as well, as I mentioned, we can only read, we can choose to read part of them. If we have a lot of small files, we can aggregate them as larger objects. So some key design integrations. So to your question, customers are using Terraform or AWS CloudFormation. For example, I'm focusing on AWS, but I'll move to another cloud in a second. But they're using these to work with WEKA. So you can just, it's infrastructure as code. You can build a cluster, you can destroy a cluster, you can expand a cluster, you can use autoscaling routes, you can use actually the Amazon Kubernetes environments. We have some integration with the AWS parallel cluster, or actually you're able to use AWS parallel cluster to run WEKA or the Nimble Studio. This is very unique. So everything that I just mentioned, and maybe I'll tie it here, is we also support GCP, as we mentioned. In production, we already are there, and you're able to, and that's unique. It wasn't transparent to us, but when we definitely compare it to other environments, there's a huge value here. You're able to grow the number of instances that you have on that cloud. Maybe I started with 100 instances and 100 clients consuming my file system or my WEKA environment, and I'm growing it and shrinking it. So I'm constantly scaling out and in the number of clients that I have. By the way, the clients are basic clients. They're not containing any metadata. So scaling out and in the clients is very simple for us. Then you can also scale out the cluster. So maybe you started with a cluster with a certain amount of instances, but then you add instances, you remove instances to the cluster, and you can do it also on GCP. And not less important, you're also able to scale in that cluster. So if I expanded, maybe I had a bursty workload and I expanded my cluster. So for us, it's just a matter of running more virtual metadata servers and more virtual data nodes on these instances. As we expanded, we can also fold them back. So the cloud elasticity is very compelling here, because you don't need to have a large cluster that can accommodate for your peak performance. You can start with your normal performance, expand and shrink.
I can say that expanding would be relatively straightforward. Is there much overhead in shrinking?
Shrinking is slightly more complicated,
yeah.
But we take that complication. The customer don't need to do it. The customer is using, for example, autoscaling group, or they just say, hey, WEKA, I need to shrink that. And we will shrink. We do everything under the hood. We evict the nodes that are not needed. We move the metadata responsibility. Obviously, if you expanded and you're using all of that capacity and now you want to shrink, we'll say, hey, you can't really shrink, right? Yeah. But we take that. So now it's a simple fact that we're now taking care of. You as a customer, you don't need to try to do anything. So we see customers trying to tackle that. What's my metadata capacity? What's my data capacity? We're doing it for them. Okay. And I would say last but not least is our ability to expand, as I say, to virtualize that capacity. But we're also able to send backups to on-prem cloud and also to remote clouds. So I haven't seen a customer still doing that, But definitely we have customers doing that and sending to remote AZs on the same cloud for cross AZ, cross region replication, or also, for example, from Amazon, you can send it to Google. From Google, you can actually send it to Amazon also. And by the way, containers, we talked about being cloud native. Containers is a big part. We have a massive CSI plugin. When you look at containers, one of our main values before I have is performance. Imagine being able to run workloads that you wouldn't consider as containerized native, high performance databases, for example, on WEKA.